Hi, I'm here to present a mechanism for intelligence. A mechanism that can find initial meaning from nothing, build that into increasingly sophisticated ideas and concepts that can potentially recreate the human knowledge that we have today and then push further beyond. So this will also be a potential mechanism for creating true AI. So let's get started with some definitions. By intelligence, I mean the ability to create a solution to a given problem. This problem can be arbitrarily complex, mysterious, and dynamic, and the solution needed may have to be increasingly large, flexible, and nuanced. But how good of a solution we can create represents how intelligent we are. As a side note, there are other ideas we perhaps also associate with intelligence, like language or understanding the world, that aren't included in this definition. But I will touch on how these other ideas may have developed in service of and their role in problem solving later in the wrap-up. Now, by problem, I mean a general goal that contains an infinite number of related but separate instances. For example, solving chess can be the overall problem, and playing an individual chess match can be a specific instance of it. Or figuring out how to hunt for food can be the problem, and hunting on a particular day under a particular circumstance can be a specific instance. With each separate instance, details change. But hopefully, there will be similarities across instances, which are what we can look for and use to create a solution. In other words, if we are facing a problem for the first time and we have no existing knowledge, then we can't create an effective solution and can only randomly guess at what to do. But as we tackle a problem again and again to see more and more instances, we can begin building up knowledge on what might work and what might not, and use that to begin creating a solution. As another side note, in this abstract, we'll simply assume that problems and instances are cleanly given to us, and we won't really worry about the mechanism of how they say form within our human existence. While tackling an instance, we will interact using actions and observations. Actions generally have some effect on the underlying world of a problem instance, though the effect can be subtle and indirect. For example, for humans, an action will be firing one of our muscles with some chosen amount of strength. Observations are data we receive about the underlying world, so input signals of various intensities, which may help us decide what actions to perform. But like with actions, they may be difficult to interpret and use directly. For humans, we receive observations, for example, through our eyes, which is data on the amount of light in our surroundings, and for example, through our touch, which is data on the amount of pressure against our skin. After attempting an instance, we'll receive a score telling us how we did. For example, for chess, we may get a score based on the outcome of a match. Or for hunting for food, our sense of hunger will essentially score us based on how full we are at the end. We may not initially understand how the score is generated, and we may in fact never fully understand it, but our goal will still be to somehow maximize it regardless. Finally, a solution is some way of utilizing actions and observations to achieve a high average score across all instances of the problem. It might include an overall plan for what actions to perform, but also an awareness of what observations to pay attention to when, and how to accordingly adjust our actions. Humans in particular can build solutions that take the form of algorithms, which is a structure that is particularly compact and scalable, and likely one of the keys to human intelligence. In the following, we'll see how this can potentially be created. We'll see how to build algorithms, and more generally, see how to build good solutions overall. To make things concrete, let's solve a small toy problem that, though small, will reflect many of the difficulties we'll face when tackling problems in general, and will also be a problem that, as may be obvious soon, will definitely want to be solved using algorithms. So let's first look at what we're initially given to solve this problem. So for each instance of the problem, we can perform any number of steps. At the beginning of each step, we'll receive one observation, which will be some floating point value. Then, we can either halt, ending our interaction with this instance of the problem, or we can perform a combination of two actions, outputting a continuous floating point value and choosing from one of three discrete options, then move on to the next step. After we halt, we'll get a score, which will either be 0, which is bad, or will be 1, which is good. And this is it. This is all we're given initially to try to solve this problem. This limited start reflects what we're often faced with when tackling new problems. And from here, we'll need to somehow figure out what the score means, what these actions do, how these observations can be used, and ultimately, how to consistently get the highest score we possibly can on this problem. But, to help make things more instructive for the audience, let's peel back the curtain to look at the underlying details of this problem. The problem solver, of course, is never given any of this. So this is actually a classic computer science problem, sorting, but on tape. Each problem instance occurs on a tape of data 2 to 10 squares long, initially filled with integer values randomly from 1 to 10. And there's a tape head, which is how we'll interact with the tape initially pointing to the leftmost square, which I'll also be referring to as the first square. At each step, we'll receive the value of the square currently pointed to by the tape head, which is our one observation mentioned earlier. For example, if the tape is currently 6, 4, 10, 5, 3, and the tape head is pointing at the first square, then for this step, we'll receive an observation of 6, the value of the first square. Then we can either halt or perform a combination of two actions, adding a value to the square currently pointed to by the tape head, which is the floating point output mentioned earlier, then moving the tape head left, moving the tape head right, or keeping it in place, which are the three discrete options mentioned earlier. For example, if we perform 1.5 right on the current tape, then we'll add 1.5 to the first square, where the tape head is currently pointing at. Then we'll move the tape head right, so our next step will begin with the tape head on the second square. One detail to add here is that the tape head is moved beyond the boundaries of the tape. There are extra warning squares at the ends, which cannot be moved past, which will return a value of -100 when read. Finally, the scores of 0 and 1 mentioned earlier correspond to whether the final tape after halting is correctly sorted or not. We receive a 1 if it is correctly sorted, and a 0 if it's not. Here, the sort doesn't have to be completely precise. As long as all the values are within 0.1 of what they're supposed to be, it counts as correct. In our current example, this final array of 3.1, 4, 4.95, 6.02, 10 has values which are all within 0.1 of the correct sort, 3, 4, 5, 6, 10. So this results in a score of 1. So in the following, we'll see how the sorting problem can be solved. We'll see how we can overcome the initial lack of knowledge to begin building a solution, and then see how to add increasing sophistication until we finally arrive at a sorting algorithm that many might recognize. So let's get started. And let's start with methods that I'll call exploring and checkpointing, which will serve as the foundation of our mechanism. So when we initially tackle a problem, we often really don't know anything. So there isn't much else we can do besides randomly trying different sequences of actions and seeing what happens. Or in other words, explore. For example, let's try this 0.2 left minus 0.4 right sequence on a random problem instance, which let's say happens to be 10, 3, 5, 3, 6, though this underlying tape is not something we'll actually know. And we get back some observations, which we won't initially know how to use, so we won't worry about these yet. We again won't actually know this, but all this action sequence effectively does is add 0.2 to the first square, which clearly doesn't lead to a correct sort, so we'll get a final result of 0. Okay, let's keep trying. Next, let's randomly try this 0.9 stay sequence on another random instance, which also doesn't lead to a correct sort, so we get 0 yet again. And so we'll keep trying random sequences on random instances, thousands, millions of times. And hopefully, occasionally, we'll get lucky and randomly try, for example, this -1 right plus 1 stay sequence, which swaps the first two squares by 1 on this 217 problem instance. This is a sequence that can lead to correct sorts, and luckily, this instance is one in which it does, and so we get a score of 1. So then what we'll do is that we'll save the action sequences that happen to have resulted in higher scores to use in the following steps, where we'll see if we can build upon them further. By the way, the reason why we have to keep using new different instances is because we cannot ever fully capture an instance to reuse. This is because we only see an instance through observations, which as we just saw, often only offers a limited view of the instance's underlying details. In addition, we only see an instance as it reacts to the single sequence of actions we try on it. We don't know how it might have behaved differently had we tried a different sequence. So because we only see an instance partially and on only one timeline of actions, we can never know the entirety of the instance, so we cannot capture it. Now, since this particular sorting problem is an artificial problem that is easy to simulate, getting new instances of the problem is easy. But it is the case that for many real-world problems, it can be costly to find and experiment on new instances. In these cases, it can be beneficial to use world modeling, where we first develop an understanding of how the underlying world works, then use that understanding to generate artificial instances to use, which is something we'll touch on more in the wrap-up. Before discussing the next step though, to help understand why it's needed, now is a good time to talk about perhaps the main existing approach, Markov decision processes, and its limitations. Markov decision processes are the foundation of the field of reinforcement learning, which is also interested in the type of general problem solving tackled here, and which has achieved some notable results. Most significantly, the reinforcement learning AI AlphaGo was the first AI to achieve superhuman performance in the game of Go, and reinforcement learning has also been successfully used in chess, video games, and so on. So generally speaking, reinforcement learning tries to model and solve problems as Markov decision processes. If modeled effectively, this will enable us to solve each step of the problem independently from any other, and enable us to solve each step in an identical way, vastly reducing the problem-solving difficulty. Specifically, when solved, we'll use the same calculations again and again on each step to select what actions to perform based only on each step's current observations and state. State here is the concept key to Markov decision processes, enabling this to work. So even though we want to treat steps completely independently, knowing past history, so what happened in previous steps, can be necessary for selecting actions optimally. So information on past history is needed. But building a growing record of history and processing all of it every step is not practically feasible. So instead, we'll compress history down into a small, constant amount of data, known as state, which will repeatedly update in each step and pass on to the next. How well we compress history into state determines how effective our modeling is. And in fact, for Markov decision processes to achieve good results, the modeling has to have a quality known as a Markov property, which is that the current observations in state need to always contain all the information necessary for ideal decisions to be made. There cannot be past history that would have mattered, but we forgot because it wasn't included in our state. Now, the Markov property can always be attained with ideally constructed state, but unfortunately, this is difficult to learn. For an AI to learn how to construct ideal state, it needs to learn what parts of history to value and what parts to discard. But as we'll see soon, this will need the AI to not treat steps independently of each other, breaking the main reason to use Markov decision processes and state in the first place. So instead, the state is often human constructed using expert knowledge, where humans identify what is important in past history, and humans then figure out how to abstract that into a small, constant set of inputs to give to the AI. This not only takes significant effort from humans, but the AI also becomes limited, at least partially, by existing human knowledge. As a result, Markov decision processes are not an effective tool for general problem solving. But let's look at this limitation more closely. What exactly happens if we try to learn state while treating steps independently? Specifically, let's look at our sorting problem. But let's not even think about fully solving sorting, but instead just focus on this simple sequence, -1 right plus 1 stay. This sequence solves problem instances where the first two squares are off by 1, so it can be a good sequence to learn, especially early on. But can it be learned by reinforcement learning? So we need to independently learn to perform -1 right on the first step and +1 stay on the second. So let's start by looking at the second step. Here, the problem is that in general, +1 stay is a bad action. Even though it can succeed when -1 right is a starting action, for most other starting actions, it cannot ever succeed. Now, this would be okay if we only perform +1 stay in the specific circumstances in which it's good, but our observations here cannot help us identify these circumstances. The only way for us to learn to value and perform +1 stay is if we already memorize whether or not -1 right was the previous action, so that we'll be able to perform +1 stay only when -1 right was the previous action, where it does have a good chance of succeeding. But let's now look at the first step. The problem is that in general, starting with -1 right is also a bad action, and there's little value in either performing it or memorizing if we did. In fact, the only way for us to learn to value -1 right is if we've already learned to value +1 stay as a follow-up, so that starting with -1 right will have a good chance of succeeding. And ultimately, because they each depend on the other being learned first, we'll neither learn to memorize -1 right nor learn to value +1 stay, and as a result, we'll be unable to learn this -1 right +1 stay sequence. And in general, when we treat steps independently, we'll miss many important synergies between steps like this, so there will be many sequences that we won't be able to properly value and learn. Specifically, unless a sequence can be built up from actions that are independently valuable, it won't be learnable. Instead, for this sorting problem, what reinforcement learning might end up learning, for example, is to start off with 0 left, an individually valuable action. 0 left makes no changes to the tape, so pre-sorted instances remain correctly sorted. Then the tape head moves off tape, so different follow-up actions that might otherwise ruin the sorted result have no effect instead. So 0 left leads to relatively high scores in general. But obviously, this traps us in a local maxima of only being able to solve instances that are pre-sorted. Now, back to our new mechanism. So obviously, we need a different approach. Instead of treating steps independently, we have to reason about entire sequences in their totality. But there's a big reason why previous approaches, such as reinforcement learning, avoid this. Reasoning on full sequences leads to a combinatorial explosion of possibilities. Not only are there infinitely different sequences of infinitely different lengths, each of which may have a unique interaction with the problem, but to handle a wide variety of problem instances, solutions need to be a combination of sequences, and there are infinitely many more of those. So in the following, we need to somehow progress through this combinatorial explosion. And we'll look at one way of doing this, which I'll call checkpointing. So obviously, it's simply not feasible to just naively explore all possibilities. And instead, we have to be smart about where to spend our effort. From our previous step exploration, we captured some sequences that resulted in high score when we tried them. Let's start by evaluating these further. While these sequences happen to score well the one time we've tried them so far, we'll want to know how they do in general. So we're going to further try them on a large number of instances. For example, for this -1 right +1 stay sequence we found from exploration, we're going to try it exactly as is again and again on random new instances. And as we're doing so, we're going to measure two things. First, we're going to measure the average score to know if the sequence is good in general, or if it just got particularly lucky the first time we tried it. Second, we're going to measure how much information the sequence gets, and this I'm going to explain in a bit more detail. So let's compare two sequences, 0 left and 0 right. These two sequences actually solve the exact same instances, ones that are pre-sorted, so they have the same average score. However, while executing, 0 right sees the second square from the tape, which will let it better predict what the final score will be before it actually halts. For example, if the first two squares are 2 and 3, then 0 right can know that it will have a great chance of succeeding, because the first two values are sorted and small. And if the first two squares are 2 and 1, then it can know that it's already guaranteed to fail, because the first two squares are already not pre-sorted. Specifically, as you try a sequence on a large number of instances, we'll learn what the average scores are given the observation scene. We'll do so using neural networks, for which we'll see the details in a bit. So when 0 right, for example, sees 2 and 3, it will hopefully have learned to expect an average score of around 0.29, which is the probability that an instance starting with 2, 3 is fully pre-sorted. And on the other hand, when it sees 2 and 1, it will hopefully have learned to expect an average score of 0. Compare this with 0 left. Because 0 left doesn't see the second square, the average scores it learns will be less accurate than 0 rights. It will, for example, expect an average score of around 0.18 both when the instance starts with 2, 3, as well as when it starts with 2, 1. Information is a measure that captures this difference between 0 left and 0 right. The higher the information, the better a sequence's observations will be at predicting the final score. Specifically, information is a similarity between the predicted average scores and the actual scores, averaged across all instances of the problem. Or practically, just across a large number of instances. But why would information be something we would want to care about? Simply speaking, high information will enable us to make good decisions. For example, if we're solving an instance with 0 right and we see 2 and 3, we know this is a situation where 0 right will likely get a good score, so we can proceed with confidence and halt as usual. But if we instead see 2 and 1, we know that this is a situation where if we go ahead and halt, 0 right is guaranteed to fail. So instead, maybe this is a spot where we should try something else? So now, we can finally talk about checkpoints. Checkpoints are spots in relatively high-scoring sequences that have relatively high information. For example, for the sequence 0 right, the point right before halting is a good checkpoint. This sequence successfully solves pre-sorted instances, so it is relatively high scoring compared to other early sequences. And as just discussed, 0 right lets us see a second square of the tape here, giving this spot a particularly high amount of information. Checkpoints will be spots that we'll want to continuously revisit as we build our solution. As we'll see soon, they'll let us reuse good sequences we've already found, while also enabling us to find synergistic alternatives. But checkpoints don't need to just be at the end of sequences. For example, let's look at this -1 right plus 1 stay sequence. Because the second action is stay, our third observation will be from the same square as our second observation. And in fact, our third observation will just be the second observation plus 1. This means that the first two observations alone already give us as much information as if we had all three observations. So instead of checkpointing at the end, we can instead checkpoint immediately after -1 right. By checkpointing earlier, we can begin adjusting our actions sooner, enabling a faster reaction to the observations we receive. So in addition to measuring information for the entire sequence, we'll also measure the information for all the prefix subsequences. Then, we'll select the best checkpoints using some heuristic based on average score, information, and how early they are in the sequence, and use the selected checkpoints in the following. But before continuing, a quick note on neural networks, which will actually be used in a few places in this mechanism. So neural networks are a convenient way to capture a relation between inputs and outputs. If of sufficient size, they can easily memorize maps from inputs to outputs, and then also offer a bit of additional generalization to roughly guess the output for never before seen inputs. Now, it is the case that there are many relations that cannot be captured by neural networks. No matter how deep or intricate the structure, the learned results from neural networks will be fixed equations, where the same set of operations will be performed regardless of inputs. And to capture Turing computable relations, or in other words, algorithms, we'll need to be able to learn results that are more computationally powerful, that can vary its operations based on the inputs. But that power, as we'll see, will come from our overall mechanism itself and its interaction with the world. So we won't be relying on neural networks to fully capture complex relations, but to simply do as best it can as a part of the overall mechanism. So in terms of network detail, we're just looking for something that is fast and robust to learn. So shallow but wide networks with simple activation functions, such as one-layer ReLU networks. Now, continuing with our mechanism, let's revisit exploration again. But this time, instead of trying random action sequences from scratch, let's try random sequences starting from the checkpoints we just found. So for example, for this checkpoint we were just looking at, we're going to repeatedly reuse the STEMI subsequence from before the checkpoint, -1 right, and try random sequences from it. For example, starting from -1 right, let's randomly follow with -1.4 stay and see what result we get. Then, starting again with -1 right, let's try following up with +1.7 right plus 8.8 left. And like previously, we'll repeat this many times, and hopefully, occasionally, we'll find sequences, like +2.1 left, -0.9 stay, that result in relatively higher scores, which we'll save and use in the following. And let's also revisit checkpointing again. And like previously, we'll try the potential sequences on a large number of instances and measure their average score and information. For example, for this -1 right plus 2.1 left minus 0.9 stay sequence we just found, we'll try it again and again on random new instances, just like earlier. But now, we can combine sequences to begin building bigger, more effective solutions. For example, let's combine our original sequence from which we found our checkpoint, -1 write plus 1 stay, with the new sequence we just found. Because these two sequences share the same checkpoint, they can easily be combined into a bigger solution, where we'll start with the subsequence they share, then at the checkpoint, flexibly choose between the two options depending on which is more likely to achieve better results. The only question then is, for a particular instance of a problem, how do we know which branch is likely to achieve better results? Remember that for each sequence, as part of measuring information, we learned what average scores to expect given what observations were seen. So all we need to do to choose between branches is to compare their predicted average scores and choose the branch with the highest. For example, here, the top branch swaps the first two squares by 1, while the bottom branch swaps the first two squares by 2. So if we see 3 and 1, we know that the top branch cannot ever succeed, but this is a promising start for our bottom branch. So our bottom branch is what we'll choose to perform here. But if we see 3 and 2, we know that instead, it's the top branch that is likely to get a good score here. So the top branch is what we'll choose instead. High information was important here, because it makes it more likely that we'll be able to make good decisions at the checkpoint. The higher the information, the more likely that we'll be able to tell when sequences are good versus when they're not, better enabling us to use sequences when they're strong and to hide them when they're weak. And by the way, if there are more than two branches at a checkpoint, to choose between them, we simply have to compare the learned score of every branch and choose the branch that has the highest score. And just like previously, we'll look for good checkpoints from where to build out our solution even further. For example, this bottom sequence, -1 write, 0 write, plus 0.9 stay, goes right yet again after the checkpoint, to see another square of the tape to get yet even more information. So this can be a good spot for a new checkpoint. And so, we'll keep on repeating these two steps of exploring and checkpointing to gradually build out a bigger and better solution. We'll use deeper and deeper checkpoints to explore for longer and longer sequences to add into our solution. Then, we'll look for new checkpoints on these new sequences from which to explore even deeper. And as long as we have effort to spend, we'll repeat these two steps indefinitely to continue improving our solution further and further. One detail to mention is that as our solution is extended and improved, we'll want to correspondingly update our learnings on the average scores given the observation seen. For example, let's say initially we are choosing between these two branches, where the top branch swaps the first two squares by 1, while the bottom branch swaps the first and third square by 1. So for the observations 3 and 2, we'll want to choose the top branch, but for 3 and 3, we'll want to choose the bottom branch. But if we extend the bottom branch to where it can both swap the first two squares by 1 and swap the first and third square by 1 depending on which is better, then for both 3 and 2 and 3 and 3, we'll want to choose the bottom branch. So we'll need to update our learnings to adjust for this. To do so, we'll need to try the entire bottom branch with its branches and learnings included on more problem instances, and update the bottom branch's predicted scores given the observation seen. But here, another detail to mention is that as we keep trying to improve our solution, we shouldn't focus solely on the same high-scoring branches, but we should occasionally also try other less explored checkpoints. For example, if our bottom branch started out with high-score information, and we've been focused on extending it, it might be that it actually leads only to a local maxima. So to prevent getting trapped, we'll want to balance by occasionally exploring for checkpoints we haven't visited as much. These might not initially have as high score or information, but it might be that ultimately a better solution can be found through them. The thing to keep in mind is that exploring and checkpointing is a heuristic. We are trying to avoid the combinatorial explosion of trying every combination of combinations, by instead building up solutions incrementally, focusing on sequences that are effective and synergize well. But because this is a heuristic, there's no guarantee that this will lead us directly to the best solution. And instead, we'll want to balance exploiting the checkpoints that initially look promising with occasionally exploring even the less appealing checkpoints, so that ultimately, we will always be able to work our way out of local maximas and progress towards the best solution. And this can be done, for example, using an algorithm like Monte Carlo tree search. But anyways, this is the end of this section on exploring and checkpointing. Through exploring and checkpointing, we're able to create initial solutions from nothing, and then find synergistic ways to improve upon them further. And we can repeat the process indefinitely to continue gradually building out bigger and better solutions. However, this is not yet enough to construct strong enough solutions needed for solving the toughest problems. So far, we're constructing action sequences one action at a time and adding them to our solution one by one, when we might need solutions containing thousands, millions of sequences, each thousands, millions actions long. And with the current structure, as our solutions become large, they'll also become infeasible to memorize, as we'll need to separately memorize every single action in every single sequence and the decision-making needed at every single branch. So, in this next section, we'll see how to overcome these challenges by adding increasing sophistication through methods of abstraction and generalization. Specifically, we'll keep exploring and checkpointing, but we're going to add methods of abstraction, where we'll look to repeatedly simplify bigger structures and problems into smaller ones. And we're going to add methods of generalization, where instead of just working with existing sequences, we'll begin building ways of generating sequences on the fly in response to whatever problem instance we are currently tackling. Abstraction and generalization will enable us to create significantly more powerful solutions. In particular, as we'll see, iterative generalization will be the key to enabling our solutions to take the form of algorithms, which is an especially efficient structure for solutions. So, let's get started. First, let's add a method of abstraction, which I'll call compound actions. So it turns out that for many problems, especially many real-world problems, combinations of actions that are useful in one action sequence can often be useful in others. For example, for humans, firing the muscles on your legs so that you can move in a given direction, which we also know as walking, is useful in many different parts of many different solutions. And for a sorting problem, zero right, which enables us to move the tape head around without affecting the values on the tape, is a combination that is frequently useful in many sequences. So what we'll do for these combinations is that we'll capture and save them separately, so that we can more easily reuse them in the future. And these saved combinations are what I'll refer to as compound actions. And compound actions can span multiple steps. For example, this subsequence, +1 left, -1 right, swaps the values of the current and previous squares by 1, modifying the tape by round amounts while preserving the overall sum. So this is also a combination that can be frequently useful. So we can save the subsequence as a single compound action that internally contains the raw actions from both steps. And the way we'll be using these compound actions is that we'll treat them effectively as new actions we can perform in addition to the raw actions we were initially given. So during exploration, instead of constructing sequences with only random raw actions, we'll also randomly include compound actions we previously found. Because compound actions have shown themselves to be generally useful, they are more likely to be effective than random raw actions, leading to random sequences with high average scores and increasing the efficiency of exploration. In addition, because a single compound action can actually represent many actions, they effectively let us explore longer sequences without having to explicitly construct them. Then, during checkpointing, we can continue to treat a compound action as a single coherent action, and avoid having to evaluate for checkpoints to look to branch from within them. This saves us the effort of having to measure the corresponding information, which can be significant, especially as the solutions and compound actions get large. To find compound actions, during exploration, we'll randomly try combinations from previously successful sequences. Then, we'll save the combinations that more frequently contribute to higher scores. For example, for this +1 left, -1 right combination in this sequence we previously found, we'll randomly, occasionally, add it into our randomly constructed sequences while exploring, and we'll keep track of the resulting scores. As we touched on, +1 left, -1 right is a generally useful combination that can be a part of successful sequences relatively often, so we'll save it as a compound action. But for other combinations that are perhaps more narrow or less consequential and contribute to lower average scores, we'll discard. For example, like the top sequence, this bottom sequence also swaps the first two squares by 1. However, it does so incrementally using more steps. And if we try this +0.8 left, -0.4 stay subsequence from the middle, this subsequence will require more specific actions around it in order to succeed, which will lead to lower average scores, so we'll avoid saving it as a compound action. By the way, The reason why we want to explicitly retry previous combinations is that it lets us know for sure that we're working with identical combinations. Otherwise, if we try to just, let's say, look for common combinations within our previous randomly constructed sequences, because actions can be continuous, we may not be able to find combinations that are equal. For example, plus 0.01 right and minus 0.01 right may be nearly equivalent in the context of the sorting problem, but they're not precisely equal, and it's difficult for us to assert that combinations that are close should be treated as equal, since that breaks near critical points, and can affect the quality of our solutions. Finally, it's important to mention that we can have compound actions of compound actions. For example, with the move right and swap by one compound actions from earlier, we can further abstract them into a single compound action that performs both. Repeatedly creating compound actions out of compound actions, then using these more and more abstract compound actions in our process will be one of the keys to enabling us to continuously scale up our solutions. This will help prevent the size and complexity of our solutions from becoming overwhelming, while still enabling our solutions to grow more and more powerful. Next, let's add another method of abstraction, which I'll call subproblems. So previously, when exploring, we've been looking for new random sequences completely disjoint from our existing solution. But now, let's reuse endings from successful sequences we previously found. So when exploring, we'll try new sequences, but add random previous endings. Then we'll evaluate as usual, but now, when we combine the new sequences into our solution, we can remerge the new branches to share the same ending. By reusing existing endings on top of our reuse of the beginnings through checkpoints, we get to keep much of an existing sequence while we explore. Hopefully, this will let us preserve the existing strengths of our solution while enabling us to further look for small, incremental improvements. This reuse is what I'll refer to as attempting a subproblem of the original problem. One additional detail we'll have to worry about, however, is that if the ending contains branches, but we change the preceding sequence, then the learnings that enable us to choose between these branches will no longer be valid. So when solving a subproblem, those will also need to be relearned. Specifically, first, when exploring, before we relearn the decisions, we'll simply choose randomly, and hope that we'll occasionally, luckily, choose branches that end up with good results. For example, if this is our subproblem, then let's construct a sequence to explore by starting with this subsequence from before the checkpoint, randomly add, say, plus 4.3 right, then for the ending, let's randomly choose perhaps the bottom branch, and see if this results in a high score. Then, for our next sequence to explore, for the ending, we'll perhaps randomly choose the top branch instead, and so on. Then, when evaluating a potential sequence, we will first try it on a large number of problem instances for each branch in the ending, to learn the scores given the observation seen. This will not only let us relearn how to choose between the branches, but it will also enable us to then evaluate our potential sequence as it's making the best possible decisions it can, letting us know accurately just how good the sequence is. By solving subproblems and splitting the merging branches, we change the structure of our solution. Instead of trees of branches, our solutions now take the form of directed acyclic graphs, which will make it cleaner for us to now add even further techniques. And for example, we can now add compound actions that include branches, which need to include both the branch split and the branch merge to preserve the abstraction where a compound action can be treated as just another individual action. Again though, when we change the preceding sequence, we'll need to worry about our ability to make good decisions for branches. In particular, in order to use a compound action with branches as a single independent action, we'll need to make sure that it contains everything needed internally to make good decisions, so this is something we'll want to evaluate as we try potential combinations. For example, let's say we have this existing solution, which moves 2 squares to the right, then decides between halting versus swapping the previous 2 squares by 1. It turns out that to decide between these 2 branches, we just need the last 2 observations preceding the branch. If these 2 observations are off by 1, then we'll choose the bottom branch to swap by 1, and otherwise we'll just choose the top branch. There's no other preceding data that's needed to make this decision optimally. This means that this smaller combination can make a good compound action. It has observation needed internally to make good decisions, while including relatively fewer actions, which might enable it to be more flexibly used across different sequences. We'll then relearn our decisions to use only internal observations, and reuse these decisions as we use these compound actions with branches across different sequences. Because only local observations are used, we can easily use these compound actions regardless of the preceding sequence, making it easy for us to treat them as singular abstracted actions and to use them in our process. And as the compound action is successfully used across different sequences, we can even try updating its decisions using data from across the different sequences to make it more robust. Up until now, we've been evaluating and adding sequences into our solution one at a time. But as our solutions grow bigger, we can now start adding methods of generalization, where we'll look for relations between existing sequences, then generalize those relations to create ways of constructing brand new sequences on the fly for whatever problem instance we're currently solving. And let's start with what I'll call continuous generalization, where we'll look for relations between the values of continuous actions across sequences. For example, let's say we have this solution, which moves one square to the right, then has to decide between swapping the previous two squares by 3, by 4, or by 6. Here, it turns out that there's a pretty easy relation between what observations are seen and which branch we'll want to choose. If the two observations we see before the branch differ by 3, then we will choose the branch with swaps at 3. If the observations instead differ by 4, then we will choose the branch that swaps at 4, and so on. So the size we need to swap by is just a difference between the observations. So what we can do here is that instead of the 3 separate branches, we can use a new structure where we'll keep the discrete actions fixed as a left followed by a right, but we'll vary the values of the continuous actions based on the observations seen. Specifically here, we'll set the values of the continuous actions equal to the difference between the observations. So if we see that the difference between the observations is 3, we will set the values of our continuous actions to be plus 3 followed by minus 3, so that we will perform a swap by 3. And similarly, we'll set the values to be plus 4 followed by minus 4 if we see that the difference between the observations is 4. We'll even set the values to be plus 5 followed by minus 5 if we see that the difference is 5, enabling us to appropriately perform a swap by 5 to solve instances we couldn't have solved before. By using a single relation instead of a potentially large number of separate sequences, there can be a lot less we'll need to remember, making solutions easier to memorize. In addition, as you just saw, it can lead us to create new effective sequences on the fly we've never tried before, enabling us to solve a wider range of problem instances than we otherwise could. However, continuous generalizations can be difficult to find. Most combinations of sequences may not be cleanly related, even if their discrete actions match. For example, here, we again have a swap by 3, by 4, and by 6, but the right action from previously has now been split into a stay followed by a right, and where we previously had minus 3, minus 4, and minus 6, that is now split into awkward combinations of 0 and minus 3, minus 2 and minus 2, and plus 2 and minus 8. Even if we can successfully learn a relation between these sequences, it's unlikely to generalize to any swaps beyond the original 3, 4, and 6, and the relation would not be worth memorizing. So to find good continuous generalizations, we will repeatedly try the following process. We will start by randomly selecting a small number of branches with matching discrete actions that will attempt to build up into an effective continuous generalization. By starting small, we are hoping to better prevent there being branches that conflict that could prevent effective generalization from being formed. Then, we'll try to build up our generalization by repeating the following. For our current set of branches, we'll first learn the relation between what observations we're seeing and what values the continuous action should take, which we'll do so using neural networks. Then, we'll see if the relation we learn generalizes to new sequences that we can add to our current set, which will let us build our generalization further. For example, let's say we started out randomly selecting these 3 branches, which are roughly swap by 1, by 2, and by 3, and we've learned a relation for them. We have luckily selected 3 synergistic branches here, but because these continuous actions are not perfectly exact, and neither will be the learned results from neural networks, the resulting relation might not be good immediately. It may successfully generalize to swap by 4, but only for some of the instances that swap by 4 can solve. For other instances, the generalization may be somewhat close to succeeding numerically, but still off enough to fail. For example, when it's C7 and 3, it may perform plus 4, plus 0, and minus 4.1 to successfully swap by 4. But if it's C's 5 and 1, it may perform plus 4.2, plus 0, and minus 4. which is close, but not close enough to be considered a success by this sorting problem. And it may completely fail to generalize to swap by 5, perhaps because 5 is further from the swap by 1, by 2, and by 3 that we started our generalization from, where again, it may be close numerically, but still off enough to where none of the instances succeed. So what we're going to do is to try our relation on a lot of problem instances to see if it leads to any new sequences. New sequences are ones which score well on instances that the current sequences in our set struggle on, such as the swap by 4 we just found, which solves instances not solvable by the swap by 1, by 2, and by 3 that we started with. If we don't find any, then we can't improve our generalization further. But if we do successfully find new sequences, we'll randomly select one and add it with all the new instances it's capable of solving into our set. Then, we'll relearn our relation to repeat these steps again. By adding a new sequence, we push our generalization in that sequence's direction. Hopefully, that leads us to a better generalization that we can build upon even further, like in this case. But unfortunately, it can also trap us into a local maxima if the sequences do not end up being quite synergistic. So it can take many tries to find a good generalization, to either have a lucky start, or to have an imperfect start luckily develop in the right direction. And now, with our improved relation, we may now be able to generate swap by 5, which can then be used to improve our relation even further. As we build our generalization further and further, the range of problem instances it can solve will grow wider and wider, and it will be less and less affected by imperfections in individual sequences, until ultimately, we'll hopefully arrive at a broad but clean relation, which here is swapping by the exact difference between the first two observations. A quick note before moving on, that by only using neural networks, there may be Turing computable relations that will be beyond our ability to learn. For these situations, we'll have to instead hope that our mechanism can find alternate action sequences that find, or perhaps create observations that drop the complexity of the relations to where they can be successfully learned, such as how humans will write temporary notes on scratch paper to help perform long multiplication by hand. But anyways, finally, we'll save our attempts that do successfully generalize to solving many instances and add them to our solution as new branches that can be chosen. And just like for normal branches, we'll learn their average scores given the observation scene, so that we can use them when they have a good chance of succeeding. For example, here, if the first two squares are out of order, then we'll choose to use our continuous generalization to swap their values. But if the first two squares are instead already in order, then we can choose the top branch to simply make no changes. And we can also include generalization in compound actions. Similar to compound actions with branches, we'll need to relearn the relation to use internal observations, and then reuse the internal relation afterwards in our process. But anyways, with this, we are finally reaching ideas that should begin to be human recognizable. This compound action here captures the idea of comparing then swapping elements if they're out of order, in this case for neighboring elements, which might look familiar from classical sorting algorithms. And finally, let's add iterative generalization, which will represent a fundamental change in the expressiveness of our solutions. When we humans solve problems, we will often repeat the same steps again and again a varying number of times, or we will wait in the same state for varying durations. And for example, in the sorting problem, by repeating comparing and swapping varying number of times, we can perform well on instances of various lengths. Here, repeating doesn't necessarily lead to solutions that are higher scoring or faster, but there's a very strong reason why we value doing so. And that is that it enables the addition of a very memory efficient structure to our solutions, iterative generalization, or more simply, loops, where we will repeat a subsequence again and again until we make the decision to break from the loop. The structure here is equivalent to this infinitely long chain of actions, branches, and merges. But instead of separately memorizing all of these individual actions and decisions, we just need to memorize the single subsequence we're going to repeat and how to make the single decision of when to break. And more generally, we don't have to break at the end of the loop, but can break from the middle. So we'll repeat the full subsequence over and over, but on the last iteration, we'll only repeat the subsequence partially before breaking from the loop. And there can also be multiple breakpoints in a loop. where depending on a specific problem instance, we may decide on any one of the breakpoints to break on. For example, let's take a look at our sorting problem again. If we would like to repeatedly compare and swap until the end of tape is seen all the way on the right, then we can just use this compact iterative generalization, which also happens to match one forward pass of the classical sorting algorithm, bubble sort. As a quick aside, bubble sort is infamous for being slow, but that's on random access memory. On tape, it's comparable to anything else. And anyways, because in our particular problem, runtime doesn't affect score, runtime won't be something we'll worry about. As we just saw, loops can make it significantly easier to memorize large solutions. In fact, they fundamentally change the expressive power of our solutions. With their addition, and in combination with our ability to impact the underlying world, our solutions are now theoretically equivalent to algorithms, which means they can now fully utilize the power of Turing machines, which are the most powerful model of computation we know, and which our human brains are potentially one of, to be significantly more expressive. Any idea that can be effectively calculated can now be captured by our solutions. Without loops, many ideas would instead require infinitely many individual actions, branches, and decisions in order to express, so would simply not be capturable, including many ideas foundational to human civilization. To find good iterative generalizations, we'll start by trying to repeat subsequences on previously found sequences, occasionally while exploring. For example, if we have this existing sequence and checkpoint, let's randomly choose this subsequence and repeat it perhaps once, perhaps multiple times, and try it on a random problem instance. If it luckily results in a high score, we'll capture it and evaluate it further in the following. We'll want to repeat subsequences from good checkpoints, by the way, because high information will likely be helpful in helping us decide when to break. Then, we'll see if we can build a loop out of the subsequence we just found. Now, a loop can potentially have an infinite number of iterations, but let's start by evaluating a small number of them. For example, let's evaluate sequences involving 1 iteration, 2 iterations, and 3 iterations. And we'll want to measure if the iterations are indeed useful at solving different instances, and if there's high information at the end that can potentially help decide if an instance should break or should perhaps iterate further. This will help us decide, for a specific problem instance, how many iterations we should perform to get the best score. For example, we'll figure out what instances score well on 2 iterations, what instances score well on 3 iterations. And for instances that don't score well on any of the iterations that we've evaluated so far, such as, for example, instances that would have needed 4 iterations, we'll simply not worry about for now. Then, if different iterations are effective, and we can successfully associate instances with how many iterations are best, we'll use those associations to try to learn the relation between the observation seen and whether or not to break. We'll do so again using neural networks, though because we'll need to handle variable length input, we'll use recurrent neural networks here. Again, we'll use easy structures such as LSTMs or simpler, and again, even recurrent neural networks cannot capture Turing-computable relations in general, so there will be relations we can't successfully learn, or we'll have to hope our mechanism can instead find alternate sequences that drop the complexity. But anyways, if a relation can be successfully learned, this will finally let us create an iterative generalization that we can add to our solution. Hopefully, it generalizes to other iterations to solve additional problem instances. Though the generalization appears useful, we can also continue actively improving it by evaluating more and more iterations to give better and better data to refine the relation. More generally, to find more sophisticated structures of iterative generalization, we can try adding random sequences while repeating subsequences during exploration, and we can try alternate breakpoints from existing generalizations. For example, if we're trying this subsequence, instead of just simply repeating it, we can try to include a random sequence as part of the loop to repeat alongside our subsequence. Then, like previously, if we happen to get a good score, we'll evaluate different iterations to try to learn a relation, and if we're successful, we'll get this generalization, where our loop will contain both the initial subsequence as well as a new random sequence and break from the middle. And for example, if we have this existing generalization, we can try to add an additional breakpoint in the middle by repeating the loop but on the last iteration, only repeating the loop partially. And again, if this is effective, this leads us to this generalization, where we'll have a new breakpoint in addition to the one from before, and where we may break out of the loop from either depending on the observation seen. And like with continuous generalization, we can include iterative generalization in compound actions, where we'll again need to relearn and reuse the internal relation. But anyways, with iterative generalization, we are now finally close to fully solving this sorting problem. Now, what we have here is just one way in which our solution could have developed, and even from here, there's many ways that our solution can develop further. But one possibility is that now that we've made our way to the back of the tape, to turn back to look for information again. While we've technically seen every square, the use of iterative generalization can make it difficult to keep track of exactly what they were. And instead, it can be more effective here to double back to re-look for information. And so we can keep moving left until we move far enough to where we can begin improving our solution again, perhaps by performing another forward pass of a bubble sort to swap more values into their proper squares. And if we keep moving left even further, we can further increase our score by being able to correct values from even closer to the start of the tape. And in fact, we might want to build another loop that repeatedly moves left to bring us all the way back to the start of the tape. And with that, we now also have what is a backward pass of bubble sort. Now with both the forward and backward pass of bubble sort, all we still need to do is to keep repeating them. Every time we repeat, we are potentially moving more and more values into the correct squares, improving the average score further and further. And so this is another good spot for us to build a loop. This time to perform the forward and backward pass of bubble sort repeatedly until perhaps the value in every square is greater than the one in the previous. Or in other words, until the tape is fully sorted. And with that, we have created what is the bubble sort algorithm and fully solved this sorting problem. No matter what instance we're facing, we will always be able to solve it with 100% accuracy to achieve a perfect score. And with that, we also have a mechanism for intelligence. We'll find initial direction from nothing through exploration, expand that into a tree of branches through checkpointing, then add methods of abstraction and generalization to build further structure and enabling our solutions to take the form of algorithms to gain the ability to capture any effectively calculable idea. My claim is that the entirety of human knowledge was constructed through an equivalent process, but I guess the only way to prove that is to use this mechanism to recreate many of mankind's foundational ideas and to then push further beyond. So there's still much engineering work ahead, and time will tell. Before ending though, let's quickly touch on a few areas that weren't covered in the main parts of this abstract. So in this mechanism, nowhere did we make an attempt to understand the problem we're trying to solve, or its underlying world. We simply went straight to constructing a solution. Yet for humans, we do for some reason find there to be great value in understanding the world around us. Separately, our mechanism consumes a lot of training data. Yet in the real world, training data is often costly to obtain, as problem instances may be rare to come by, and failing in real life can have severe consequences. So these two thoughts are actually likely connected. By developing an understanding of the world, we may be able to, in a way, simulate the world mentally in our minds to create artificial training data that can be used in place of real data to help create solutions. Specifically, for a particular problem, we'll need to be able to predict the upcoming observations no matter the situation, and given any combination of actions we're thinking to try. And in general, this will be too difficult. It will be infeasible to independently capture every minute detail of the world, then separately predict how each detail will change given an arbitrary combination of actions. But what we can potentially do is to model the world as a limited number of objects or events, each of which broadly encompass many details about the world, so that we only have to predict how our actions affect this much smaller number. For example, instead of separate bits and pieces, we'll learn and track, say, a car as an object overall. Or instead of individual raindrops, we'll learn to understand the event of rain. This will require us to learn increasingly complex structures, variations, connections of objects and events, how to recognize them, how they change based on our actions, how they interact with other objects and events, etc. As can probably be imagined, this is a complex problem that will require its own separate study and won't be tackled in this abstract. Next, this abstract focuses on innovation, how to tackle completely unknown problems through creating brand new solutions independently from nothing. However, it's often much easier to learn existing solutions from others. We can bypass the cost of experimentation, the cost of failure, and directly learn what others have found to work in the past. Most directly, to learn someone's existing solution, we'll copy and evaluate different action sequences they perform across different problem instances. This way, we'll get to start directly with effective full sequences instead of having to slowly build up through trial and error. And seeing others choose specific sequences in specific circumstances can help in our evaluation of these sequences. Humans, of course, are also able to share solutions through language. Language certainly has other uses, but by naming actions and objects and events, we can effectively share action sequences and when to perform them with each other. The human civilization we have today was built up through the trial and error from uncountable human lifetimes, and language has been a key enabler of that, letting us continuously work together on a shared foundation. Finally, understanding intelligence will not only let us gain a deeper understanding of ourselves, but will potentially also let us create new forms of intelligent beings. But how might true AI relate to and impact humans? So AIs, at least the ones directly resulting from this abstract, will not be theoretically more intelligent than humans. Both will be Turing complete, with the ability to create and utilize algorithms, so any solutions discovered by AIs can be shared, understood theoretically, and utilized by humans. However, in contrast to humans, AIs can be fully cloned. Whereas we cannot go inside a human's brain to copy or change the configuration of the neurons within, AIs are digital, which means that we can directly copy their entirety, including every individual weight of every neural network used within, and clone that into new AIs. This means that instead of having to go through the decades-long growth and learning process necessary for humans to begin reaching their full potential, new AIs can reach full development instantly. And by repeatedly copying themselves again and again, AIs can be effectively immortal. They can continue to pursue goals and acquire knowledge across physical forms. In addition, AIs won't be tied to human biology. They can potentially be smaller and more specialized, larger with more concentrated computational power, or engineered to operate in circumstances where humans cannot survive. The new capabilities potentially brought by true AI will likely dramatically change society that's currently shaped around our human characteristics. There will be a further increasing number of areas that will no longer be solely dominated by biological humans. So facing this potentially changing future, what should we pursue as the future of humanity? First, as mentioned, the ability to clone themselves, to access and modify their internals, may be perhaps a main competitive advantage AIs will have over humans. But if we can somehow advance in the field of cybernetics, to perhaps create, say, cyberbrains that can be digitally accessed, but can otherwise work similar to and in combination with our biological brains, then humans might be able to match this capability as well. Second, it's taken millennia for humans to build up to the civilization we have today. And AIs will, at least initially, likely want to build off of human achievements and ideas. In doing so, they will essentially share our human history and culture. And perhaps, instead of thinking about them separately, we should view AIs as another aspect of humanity. Human history has been one of overcoming limits, to continuously rise above our environments to grow to something greater. In the coming future, humanity will, of course, face further challenges. Perhaps it's the carrying capacity of Earth, or that of crossing the vast boundaries of space. And we might need to go beyond our human biology, perhaps through cybernetics or AIs, to rise to the challenge, to push humanity to even greater heights.